In this video, I'm going to demonstrate how we can use actual causality to explain proofs. To showcase this idea, we use the game of tic-tac-toe. For our purposes, we will be playing as O, and our opponent X will be playing optimally. As you can see, the opponent's winning strategy can be represented by this formula, where each existential quantifier represents a move for the opponent over all possible moves for us. Here we have one line of play from a given starting point, where despite X's optimal play, there's a way for us to avoid a loss. Our goal in this demo is to explain such proofs. Causality is the science of causes and effects. We use Halpern and Pearl's framework, which focuses on counterfactual reasoning, where the presence of a cause in the actual world will result in the effect, and the absence of a cause will not result in effect under the same contingencies. By identifying an actual cause of an effect in the system, we provide evidence for two key points. One is the actual world, where the cause occurs and the effect follows, and the other is the counterfactual world, where if the cause does not occur, alternative events prevent the effect. Using the actual cause obtained from this framework, we can clearly explain the validity of the proof. As an example, take this board position where we start after our opponent selects the top left position. The effect we're interested in explaining is where we can avoid a loss. Actual causality tells us that placing our piece in the very center of the board, we have a line of play which can prevent our opponent from winning, but any other move would result in a loss. One such counterfactual is shown here by placing our piece in the top right position instead. You can see as these two lines progress, even if we play optimally after this move, there is no way for us to prevent a loss to our opponent. The overall structure of our demo consists of natural language input from the user, which we used the large language model GPT-4o to extract the encoding from this query and provide it along with the state of the board and our formula to an SMT solver, which ultimately provides a response to the user in natural language. Now, let's show some examples in our demo. From this board position, we only have one move that prevents us from losing immediately. Our only option is to place our piece in the top middle position. Therefore, in this case, this move is our cause for the effect of avoiding defeat. We can ask the demo a question such as, what move should I play here? And you can see that it recommends the top middle position. Alternatively, you can ask questions such as, would playing bottom middle be a bad move? And the demo will use the counterfactual to respond. From this board position, the only move that can prevent a loss is the very center of the board. Every other move allows our opponent to guarantee a win. These moves are counterfactuals, where the center is our cause. We can ask a question, how can I avoid losing? And the solver will identify the correct move as the cause. If we ask a question such as, why shouldn't I take any moves in the bottom row? And you can see that the solver will provide the counterfactual for each of the potential moves. Some ideas we would like to explore in the future include explaining the quality of proofs, where a metric such as the length of the proof can be used to compare multiple proofs, forward-looking questions up to a certain bounded horizon, different causal models and changes of assumptions in different proof steps. Using the tic-tac-toe example, this would be changing the opponent's strategy, and incorporating ethical and situation-aware decision-making in proof steps. Thank you for watching.